All right, what we're going to do now, you may want to cry looking at this. What I tried to do is I was going through trying to figure out how am I going to communicate to you the way that you sort through internal flow problem classification. So this is my attempt, and hopefully it'll be not as bad as it looks. What am I doing? So what we're doing, we went through the external flow classification, right? We say, okay, is it laminar, is it turbulent? What kind of geometry is it? Is it fully developed? Is it not, right? There's all this stuff that we have to think about. So for internal flow, the layers that we have to think about are even more, right? It's not just like external flow where you're looking at sort of one thing. Now we're looking at a couple other things, like whether you transition to turbulence before you're fully developed or not. And then once you make all these determinations, you have to find the right correlation that goes with your situation. And it turns out that there's some situations where, like it's internal flow, but you actually model it with an external flow correlation. So, okay, all this is really confusing and hard to communicate. So hopefully maybe this will clarify things a little. So this is a flow chart. So what I want to do is just draw the connections. All right, so what we're going to do is we start in the upper left. This is the method that you would use to decide which correlation features you need. So in the end, let's say I need a correlation that's laminar, external, and provides a local value. So which conditions here would lead to that? All right, so to start off, what we're going to do is, the first thing you always want to do for an internal flow problem is compute the hydraulic diameter and the average velocity, right? This is the average velocity inside the duct. So we do that, and we'll use those then to feed into our Reynolds number calculation. So you have your DH, you feed that in, you can compute the Reynolds number. All right, once you know the Reynolds number, then you can make some determination here. You can make some determination about whether or not that Reynolds number would lead to laminar flow or would lead to turbulent flow. Right? And remember, if it's going to be turbulent, it has to do so before that fully developed region. We can compute, if we compute that the Reynolds number is greater than 2300, then it will become turbulent before that point. Okay, so let's maybe start on the top here. We'll draw some lines. So let's say that we compute Reynolds number is less than 2300, so it's not going to be turbulent. So then the next step is we need to figure out where is this thing become fully developed. All right, so it's going to become fully developed, let's see. So I'm going to compute where this becomes fully developed using this FDH. And then I'm going to say, like, am I looking at a position that's before it's fully developed or after it's fully developed? All right, so let's say we're going to look first after it's fully developed up here. If I look at that, then I need to account for the duct shape. Right? The shape of this internal enclosure is important, which implies in the other cases it's not, right? So it's important here. So then I ask myself the question, am I looking for an average value or am I looking for a local value? So either way, I guess we could start with the average. So if I'm looking for average, then we go up here. Then I ask the question, is L much greater than the fully developed length, right? Can I neglect that entry region? So if I can't, then I go up here. All right, so then I have a correlation that has to include duct shape, it's internal, it's a laminar correlation, and I'm integrating the correlation, right? It's an integrated value. All right. Moving down, if I said yes here instead, now I have to have duct shape, internal, laminar, and use the fully developed value. Right? So if you think about what I'm doing there, right? We're saying we can go way beyond. I'm just going to use the fully developed value. All right. If I went down, let's kind of step backwards here. So let me just say, so I'm stepping backwards here, and I'm going to do the local, this local here. So local, it turns out I can use duct shape, internal, laminar, fully developed value. All right. Okay, so presuming that branch all makes sense, now let's step back here to the XFDH. So let me look at this. So now if I go back and I'm looking at an X position that's before the fully developed, so I'm still in the entry region. Now I need to ask whether I'm looking at average or local. Yeah, is there a question?
Don't we need to multiply the REDH 16 by LEDH?
Yes, yep, thank you. So that would be X times here, D sub H. Thank you. Okay, so X, we're now in the entry region still. So I'm going to ask, are we looking for an average or a local value? If we're looking for an average value, then I'm going to go laminar, external, right? I'm still in the entry region, or developing region. So laminar, external, and I'm going to integrate the value. If it's local, I'm going to go down here. Laminar, external, local value. All right? So, okay, that branch should be resolved. Now let's say I'm going to go back to this position here and look at Reynolds number is greater than. So this is now turbulent flow, or it will be turbulent at some point, right? So let's figure this out. So yes, so now I'm going to go down here, and now I'm going to compute where it's going to be turbulent, all right? The whole point here is we're trying to figure out where we live in the world. We know that there's turbulent, but we don't know if we're there yet, so we have to compute that location. Okay, so now we compute X critical, and let's say, are we before or after X critical? So let's say we're before. So now I'm going to ask, am I looking for average or local? If I'm looking for average, well, it turns out I'm going to use laminar external integrated correlation, right? The same one as above. If I'm looking for local, I'm going to use laminar external local. So those actually end up lining up there. Okay, going back to the critical, so now let's say I'm after, X is after the critical X position. So I need to now incorporate relative roughness. So this is something you have to bring along, kind of like duck shape. I'm going to ask myself average or local. If it's average, then I compute is L much greater than X critical. If not, then I'm going to use turbulent internal relative roughness integrated correlation. If it is much greater, fully developed value, right? So fully developed value, remember that's just the local value, but at the fully developed region. Okay, then the last thing is relative roughness, so local. So looking at this one, this actually ends up being here as well. Okay. So in years past, I've taught this. I've just done this basically by writing a bunch of stuff out, which is even worse than this. So hopefully this is better. But this at least gives you an idea of like, okay, I'm going to walk through this process, follow the steps, and I'm going to get to a correlation that matches my situation. Are there any questions on?
Yeah, so when you're deciding if X crit is greater than, or if X is greater than or equal to X crit, what X are you talking? So
let's say we're looking at, we're trying to evaluate like the local condition at a certain point. So if we know we're looking for a local condition at a certain point, X would be that position. If we're, let's say, looking for behavior over a full length of a pipe, then I would just say X equals length, right, L. And then that would be the thing I would use to evaluate. So X is kind of it's our variable to just say, like, what's the total length we're looking at in that situation.
What's the criteria for differentiating between the average and the local in these situations?
Yeah, so like if you're trying to decide what, by criteria, do you mean like applications or? Yeah, so if I was trying to decide like what's happening right here at this spot, let's say I care very much about not exceeding the temperature, like in the heater problem, I care very much about not exceeding the temperature at some spot. You have to do the local because you need to check at all the local positions that the temperature is not exceeding a certain spot. So it's all about like, do I care what's happening kind of at a specific location, or am I just trying to get a big picture of what's happening overall, right? And that's going to be the average versus local. Okay, so this is kind of how I want you to think about classifying it. Let's go through and, where am I on my notes? Let's go through here and think about how to use these correlations.